Well, thanks everybody for being here. It's a great pleasure to introduce Professor Sabrina Maniscalco. She is the CEO and co-founder of Algorithmiq, and she did PhD in Palermo in Italy, postdoc, and one in Bulgaria, one in South Africa, one in Finland, and then afterwards she became professor in Edinburgh in the UK, in Scotland, actually, in Heriot-Watt University. Then went back to Finland as a chair of theoretical physics in Turku in Finland, and then since 2020 has been professor, dual appointment at the University of Helsinki, main appointment also at Aalto University, both in Helsinki, nearby. And then in 2020, she co-founded a company called Algorithmiq. It's about 45 people, the company. She has done great work in different areas of physics, including non-Markovian open quantum systems, quantum optics, quantum information, quantum simulators, quantum computing, etc. And today is going to give us a talk about making quantum matter, a case study in application-driven quantum computing for chemistry and life sciences. So welcome very much to be here.
Okay, very nice. Thank you. Just a second. Meanwhile, I can say that it's really a great pleasure and an honor to be here. I'm very happy, and you can hear me, I guess. I'm very happy and excited. And I'm also happy because I'm going to share with you something that we do in Algorithmiq. And I hope that there will be really, my main message will be if there is something which you find useful and resonates with you for your work, to get in touch. I think that this would be the most important thing. What I will tell you first is what Algorithmiq does. And for doing this, I have to tell you our mission. We develop quantum algorithms and software that makes quantum computer useful. Now, what this sentence means will become clear once I tell you some of the example use cases and applications that we have been considering. But however, importantly, since the very beginning, we selected as our vertical, as our main field of application, chemistry, materials, and in the long term, healthcare and life sciences as the vertical where we believe there will be one of the largest impact of quantum computers. But now I have to introduce Algorithmiq, and I will do it very briefly, giving you some numbers. Already before, Franco mentioned, founded in 2020 together with 3 researchers in my group. The top company is a Delaware company. We have headquarters in Finland and offices in London and Dublin. We raised over $20 million, $5 million in partnership value. What is most important is 9 patent applications. For us, what is key is to protect those parts of a quantum software pipeline that we believe are key for scaling up. Scaling up means going towards larger and larger use cases. Over 60 publications. This means that clearly, since when we were co-founded, clearly we are targeting and we are doing a lot of research because this is also very necessary at this stage. 2 products, Aurora and the digital quantum interface, 42, now 45 employees. Many of them really, not only in quantum physics, but also in quantum chemistry, computational biology, but all at PhD level. So I told you more or less, these are the numbers. This is the core of the company. So, but most importantly, what is one of the main messages that I want to achieve now? And one of the main messages can be summarized in this way. It takes more than cool hardware and clever algorithms to make quantum computers useful. In fact, it's extremely complex. And I think that some of the complexity, some of the difficult parts in the pipelines, which are often overlooked, should be more exposed to understand actually how to operate at the level of quantum advantage and beyond. So I want to convey this message, and I hope I will go back to this over and over again. But before that, let's consider why the attention on quantum computing in particular. It is believed that quantum computers will be the so-called next exponential technology. So this means basically that because we live in a society where everything relies on the speed and the ability to compute, then obviously who owns this technology will be able, oh, I noticed that there is, let me just do, if I do like this, no, I will have to move it a bit. I just want to, oh no, I cannot do it. Maybe, okay, never mind. It's okay. It's just that it overlaps a bit with the slides, but it doesn't matter. So, and what we do in a company like Algorithmiq is that we have to balance somehow 4 pillars, okay? One pillar is R&D and product, okay? R&D means everything that we develop, fundamental, and the product, how we productize it. The other part is the business, because as a company, obviously, we sell something, we have to have a product, and there should be a market, you know, and there should be what normally in the startup world is called the product market fit. So the fit between the product and someone, which are buyers that want to buy the product. The team, important, especially now, because you have to have the top level experts in different fields that are at the core of the company. And very importantly, the timing, because the timing has to be right in order to have all these 3 things work synchronously to achieve something which will impact society as one wants to do. And then we'll talk about specifically about 2, why? Okay, yes. The quantum advantage question. So, of course, I will divide it into scientific and commercial. So what is the quantum advantage question? As you know, one of the reasons why the full quantum ecosystem has been developed is precisely because we know that for certain categories of problems, quantum computers can outperform a classical computer, in some cases dramatically, really providing exponential speed up for certain categories of problems. However, it has not yet been proven that for something useful, this happens. It has not happened in the lab. So we are still waiting to show that for a scientifically relevant problem or for a commercially relevant problem, quantum advantage can actually be achieved. Okay? And this is obviously because we know that from the classical perspective, we are actually competing with the classical computers that are very old technology, so they are way more advanced. So there is this current attempt for demonstrating what will be an inflection point in quantum computing. And I think that perhaps the main question that we all really stakeholders from academia, from companies, from governments, from investors, from industry, are really asking, at the moment is, what is the level of maturity of quantum computers? I mean, how mature are they as a technology? Are they something which is still, belongs to the labs, or are they a technology that can be really productized and therefore used for impacting society at large? And here I listed a number of equivalent questions, okay? If you want, really, the last one is what I just say, is quantum computing a research field, an emerging industry, or already a disruptive platform? So this is a key question everyone is asking today, okay? And what is the answer to this question? Well, I believe that actually the key question that people should be asking is, who truly owns the answer to this question? Who knows it? Who knows the level of maturity of quantum technology? Who is able to say, how close are we to scientific or commercial quantum advantage? And I believe that actually, to be honest, there are very few people who can say this. Of course, the people who are developing certain quantum computers, and I mean, I tell you this as a provocation, clear provocation, but it is something which is really requiring to be able to operate quantum computers at large scale and to ask since the very beginning, how do the algorithms and the use cases scale? So not just with few qubits, but how can I scale them to hundreds of qubits, to thousands of qubits, okay? And this is not just a hardware question. My take is that very much also a software and algorithm question, okay? That's my background. What I will try to do is I will try to give you some examples concrete examples of what are the key ingredients that are part of all these 4 pillars, and they aim at identifying the time and the, if you want, blockers for scientific and commercial quantum advantage. So this will be the topic of my talk, okay? I go from the general overview of we as a startup and how we operate to practical examples that ideally will indicate, what it takes to answer to this. And importantly, when you are in this balancing act between all these different points, your focus keeps shifting. And it keeps shifting because still we hear and we notice that the technology keeps shifting. So it's a very dynamic system. It's a very dynamic process. And that's why startups that are very fast in operating, let's say, have their role within the quantum ecosystem. So when it comes to, I was having lunch today with some colleagues here, and we were discussing about, okay, how exactly this question, how easy it is, how far are we to quantum advantage? And really, the main point is to identify, since the beginning, the key blockers, okay? What are the key blockers to actually scale up algorithms? This is just for the scientific part. But the other one is, what are the key use cases? What are the key applications? What are the key verticals that will mostly benefit from quantum computers? You need to have answers to both of them. And what I will talk about, because this is the topic of my company, is quantum simulations of materials and chemical compounds, but I will also give an example of a topic that is of scientific relevance within the field of quantum chaotic systems. But now, for quantum simulations of materials and chemical compounds, one can ask or investigate blockers to quantum advantage for near terms or for future fault-tolerant quantum computer. And here I want to mention some, because some of them are quite, so to say, obvious to you. Others may not be so obvious, okay? The most obvious of all is noise and errors, right? So we do know that quantum computers are faulty, that noise is creating errors that needs to be corrected or mitigated. And this is one of the main problems that everyone is facing. But another problem, which is very often overlooked, is the fact that, to measure properties of a chemical compound or a material, you measure observables, right? And you have to have sufficient statistics. So the number of measurements that you need to perform in order to achieve a sufficiently small errors to be meaningful, can be tremendously large depending on the problem. So how you measure a quantum computer in order to have really small errors is an often overlooked problem that needs to be considered. And also initializing the quantum computer in the right state. If you want to do a simulation of a quantum chemical problem, you need to be able to really input in the quantum computer an ansatz, so an initial circuit that is as close as possible to the molecule that you want to simulate. So, and this is, again, it's non-trivial when you look at, when you consider at scale. Comparing with classical methods, that's another important thing. So you not only want, for quantum advantage, you not only want to have the best quantum simulation algorithm, but also you want to compare it with the state-of-the-art algorithms, which are continuously advancing. Benchmarking, you have to be able to prove that actually your simulation is meaningful. So you have to have some regimes of your simulation where you know the answer, okay? So that you can compare, with an analytical solution or a simulation, and you can make sure that it's meaningful what you are expecting, especially when you go beyond what it is classically simulable or known. Physical meaning, at least for the scientific quantum advantage, you also want to operate in a regime in which you solve a physically meaningful problem. It's not just a problem that showcases, the capabilities of quantum computers. And of course, there is also issues related to signal strength, very technical point. Your signal cannot decay too fast because otherwise you will not be able really to observe any comparison or any difference with the classical methods. Extrapolations, you want to have a category of problems for which the answer cannot be simply extrapolated from the finite size scaling. So many, many, many technical issues that need to come together that you need in practice to solve if you want to have a meaningful scientific quantum advantage technique. So as you see, some of these points, they have to do with improvement in hardware and software. Others are really more practical, empirical even, where you need to have algorithms and software that need to be used at all levels in order to achieve something that is a quantum advantage at scale. So what we do in Algorithmiq is we have two different products. One is a digital quantum interface that is more low level. It's a middleware, low level in the stack, where we optimize the readout, we optimize the measurements, we transpile, compile, error mitigate. I mean, all these parts are proprietary. And then we have a higher level product where we do quantum simulations of chemistry and materials and also life sciences. What is very important is that I will show how these two need to be co-designed and co-optimized together in order to have something which scales. If you don't do this, it will be impossible to operate at large scale. Okay, now you know all about, so I will, my plan is to first analyze a use case that is for condensed matter physics, and I will explain in particular how the error mitigation works at scale and what is error mitigation. And the second part of the talk will be more on the use case that has to do more on chemistry and life sciences, in particular actually to drug discovery. And so we will see how all the parts need to come together. So again, two applications with in mind the question I asked before. What does it take actually to scale, to go towards quantum advantage in both cases? So let me start with very, very brief, super fast distinction between error correction and error mitigation. Error correction is, of course, much more well-known than, or at least is considered, and it is reasonably what will be needed in order to reach very, very large use cases of industrial relevance. And in error correction, what you generally do is work with logical qubits, for which you need many, many more physical qubits in order to implement one logical qubit and many gates. So normally it's considered to be even thousands of physical qubits that are needed for logical qubits. And of course, this is currently an issue just because the existing devices don't have that large number of physical qubits. And then instead, for error mitigation, which is what I will focus about here in the following, you use physical qubits. So physical qubits are logical qubits. So I will use the qubits of the device. But all error mitigation methods, they require, or they necessitate so-called repetition of measurements. So you have a sampling overhead, because eventually to use error mitigation methods, you will need to repeat many times measurements in order to reduce the statistical error. So contrarily, so if you want, it's a very different type of resources. For error correction, which is ultimately what you would need, because it does not require an exponential overhead like error mitigation, you need more qubits. And more complex operations, while for error mitigation, you can use the physical qubits, but you need to sample many times. And one of the issues is that for quantum error mitigation, the number of samplings that you need is actually still exponential. So this is a problem. This is why for a long time, error mitigation was considered actually not useful, because you still need to repeat actually you have an exponential overhead that is here represented in that curve there. So you have a computational cost as a function of the circuit size, which scales exponentially. Now the point is that if you want, this is the formula. Okay, maybe I have to use my pointer for those who are online. So here is the formula which give you, in general, the minimum sampling overhead. And this is epsilon is the average error rate, and n is the number of qubits, and L is the circuit depth. So as you can see here, if you put the numbers for realistic numbers of epsilon, n and L equal to 100, you can actually estimate what is the overall sampling overhead, and you can perform realistic resource estimates of what you can actually implement on quantum computers with today's machines. So you see that, for example, if you fix or if you allow for an error for estimating a given observable of 5%, then you will need overall of the order of 10 to the 6 shots, measurement shots, and this means in practice that you will, your experiment will last up to 73 minutes. So you can really concretely make estimates of, and these numbers, for example, 10 to the 6 or 10 to the 7 are compatible with certain physical architectures like superconducting qubits. They are not, they are much less compatible. Indeed, these numbers that you see here are for superconducting qubits. Instead, if you use other platforms like trapdions or neutral atoms, they become prohibitive, just because clearly for trapdions and neutral atoms, the duration of gates or also duration of the sampling is much longer, okay? So, yes.
Can you please remind us briefly the abbreviations PEC, ZNE, TEM?
Yes, sorry. I mean, don't, this one you just perhaps don't look at it. It's just to me. So in general, I can say it. PEC is probabilistic error cancellation, ZNE zero noise extrapolation. So what this means is that these are two of the error mitigation method. Both of them, I think, proposed and used by IBM. These are they are, as you see, depending on the error mitigation method, you have a different actually for PEC is really a different exponent. There is a factor of 2 here. For ZNE, instead, there is a coefficient which scales quadratically with NNL and epsilon. So, I mean, generally, instead, for the tensor network error mitigation that we have developed, that we propose, instead, the sampling overhead is much lower. In fact, it's optimal. So it gives the minimum sampling overhead of all possible ones. So but at this stage, I just wanted to, because I will not go in depth into the error mitigation method, but it's just to tell you that it is exponential. You can calculate from this sampling overhead actually the resources needed. So that's the main message. And of course, there are different methods, and what we have developed is an optimal tensor network error mitigation. So this is the key message of this slide. What I want to point out is that some time ago, actually last year, no, this year, very recently, we have, together with many other researchers from, okay, there is IBM, Google, AWS, and it's a large group of people. There is NVIDIA, there is, of course, EPFL. So it's a large group of scientists. We wrote a paper called Myths Around Quantum Computation Before Full Fault Tolerance, what no-go theorems rule out and what they don't. So in this paper, we demystify some assumptions that were directly, very often considered as limiting of near-term quantum computers. And one of them is related to error mitigation. And the idea is that many thought that error mitigation just cannot be used because of scalability limitation, basically because of this exponentiality in the sampling overhead. While instead, of course, it is possible to prove that it's true, it is still exponential, but it depends on the exponent. So if you really study the exponent, which is this epsilon and L, and you understand what is, of course, from the hardware perspective, what is this epsilon, you can estimate really the maximum circuit size that can be implemented or corrected using this error mitigation method. So something can be done. This is the main message of this. Now, as we proceed, I will just mention briefly one of the applications of error mitigations, and this application has to do with our own technique that we developed at Algorithmiq. It's called Tensor Network Error Mitigation, or TEM for short. And this is a technique that uses actually tensor networks in post-processing. This is the references are down there. Tensor network in post-processing to remove errors. And it's exactly what gives you this lower bound that I mentioned before in terms of sampling overhead. So the application that we studied here is an application of quantum chaos on quantum computers. And in particular, we demonstrated that we can calculate, or we can study 2-point correlation functions at infinite temperature. So it's a problem, it's a quantity which is generally studied by this field. And we can show that if as you can see here, what I'm showing here is the signal, so the 2-point correlation function as a function of the circuit depth. And in particular, these results are for 91 qubits and 91 layers of CNOT. So overall is 4,095 entangling gates. So it's actually quite a large, massive circuit. And you see the yellow line is the line in which you just look at the output of the quantum computer, while the green line is the error mitigated result. And you can see that it goes well in, in accordance with the targeted result, with the theoretical results. So in particular, obviously, this is a case in which we have a clear benchmark. And I will just show very brief let's say, additional example of what it is this in more detail, which type of gates we implement and how it is done. And then I will move to the case of chemistry and life sciences. But for this, really, the most important thing is that you remember, Franco, you asked before about what is PEC, what is GNE. When we notice for this specific example, we can see that we can enable 500 times speed up in computation is precisely because if we compare it to PEC and GNE, we can have up to 500 times faster overall. This is the whole time of the algorithm. With respect to the other methods. And 500 times really makes a difference between what can be done and what cannot be done with these devices. And of course, because this is a tensor network method, it can be highly parallelized, it can be run in GPUs, and then you have additional speed up. This was a collaboration with IBM and Trinity College Dublin, and this is a very busy slide, but I want to very briefly give a tiny little bit more information about, this is very similar slide that I showed before, about the type of circuit that we implement. These are a brickwork circuit, and to calculate this function, is an infinite temperature correlation function. We have to implement initially a state which is similar. We use some tricks to really implement a maximally mixed state, a state similar to a given temperature state. And then we start using these unitaries that are basically decomposed in these sets of gates. So you have, let's say, the X term, the Z, X rotation, Z rotation, and this is, of course, the entangling gates. So generally, in quantum computers, the entangling gates doesn't have a parameter, so this J is fixed. And you change B and H here to change the parameter space of this model. And depending on the values of B and H, you can really identify some points in which the system is analytically solvable, and some points in which the system actually is not analytically solvable, but can be simulated, okay? And so you have, these points are your benchmarks. These are the points in which you want that the result of the quantum computer really coincides with something. And you need to benchmark, because otherwise you don't know if what you are doing is actually meaningful or not on the quantum computer. And then you go away from these points in order to explore regimes where it is hard to simulate, where you don't have really, in a way, any, you don't have any exact results, and you have to use approximated methods. So this is just what I wanted to mention here. And in particular, I will just show this slide very briefly to see how this look like, and I will give two main messages. This is, by the way, the paper. It's called Dynamical Simulation of Any-Body Quantum Chaos on a Quantum Computer. And you see here, this is the IBM device. This is the topology of the IBM device. Here you see colored the qubits that are used for 51, 71, and 91 qubits. And one of the points I want to make is here. Okay, let's look, for example, at these sets of results. This is just an example in which, if this parameter is at the center, okay, you want to benchmark the results of the quantum computer, which is here, with the results of the error-corrected method, which are the green dots. And then the other two lines that you see here are the state-of-the-art tensor network methods in two variants, okay? One is, so this one up here is so-called a simulation in the Schrödinger picture. So if you just do tensor networks as in, normal dynamics, okay? And the other one instead is a more refined Heisenberg picture tensor network method, which in this case performs better. So you see how in a regime in which you have no exact method, you're testing the limit of classical computational techniques, you see that the quantum computer and the Heisenberg tensor network simulation give consistent results, while the Heisenberg tensor network simulations is way off. So this is what people refer to as a utility experiment, just because we are you're comparing really approximate techniques, and the quantum computer helps you to understand which of these simulations might be the right one, just because you find agreement and which one may not. Yes?
What is better, Schrödinger or Heisenberg?
In this case, the Heisenberg simulation method is better. It is, there are many reasons to believe that this is the right, it coincides or converge with the quantum computer. And there are reasons to believe that, I can explain why it is better. It's just the structure of the circuit. It is easier to simulate when you look at the observables, so from right to left rather than from left to right.
Interaction picture?
Not really. I don't know why people don't do it, but yeah, this is a good point. Okay, now this is, and now we go back to productizing this. So TEM is in itself is something that we have developed and we use in our work, but it can also be used by anyone using IBM quantum computers, because it's also a product. It's really a line of code that you can call from the Qiskit function. So it's a Qiskit function. It's again, role of startups is to take some tool that is useful, in this case, error mitigation, and making it into something that others can use. So TEM is now available as one of the Qiskit functions, and if you're interested, it's easy to, for 3 months, it's absolutely free, and we help developing use cases for TEM. Now, let me go back to the second part of the presentation, and the second and final part will be about more related to business, so more related to applications that can give an impact, that can have really commercial value, okay? And it's more our long-term goal as Algorithmiq in healthcare and life sciences. So the very first important point here is that there are 3 points that need to be considered. First of all, you have to have an end user which has a need, okay? A problem that needs a solution. That's always the case. You can't, just do something because you can, but you also have to additionally solve a problem for a certain industry, right? Then you have to consider how hard it is to simulate this problem classically. Remember, you still want to prove that you have a solution which is better than the classical one. And then you have to consider how it scales, because obviously, eventually you want to be able to demonstrate the same use case for larger and larger, and therefore more and more complex systems. And then, of course, you have to assess the feasibility on quantum computers. And I will, in the use case that I'm talking about now, I will consider all of them. The use case that I will present is an application of photodynamic therapy for cancer treatment. First of all, this is a partnership with IBM and Cleveland Clinic. Cleveland Clinic is the end user. So Cleveland Clinic and medical doctors in Cleveland Clinic and bioengineers in Cleveland Clinic have a problem. The problem is related to photodynamic therapy. So what is photodynamic therapy? Photodynamic therapy is an alternative therapy to cancer. As you know, cancer has, unfortunately, many side effects. Therapies for cancer, like chemotherapy or radiotherapy, they are very invasive. They are very heavy on the body. And photodynamic therapy has the positive side that it has very little toxicity. Why? because the patient ingests a photosensitizer, so a drug which is not active, so it's not attacking the cells, but it becomes active upon interaction of light. So imagine that you have a skin cancer or even bladder cancer or stomach cancer. So you ingest the drug is absorbed by the cells, and then it is only activated in the location where the cancer is, okay? So then the active drug starts to attack the cancer cells and therefore to kill them, okay? And the problem that our colleagues at Cleveland Clinic told us is that photodynamic therapy is very hard to implement in practice because there does not exist a computational pipeline. So what you do for developing this type of drugs and to optimize them, you have to do it in the lab. So this means really, it is really trial and error very often. It's a very, very cost inefficient and time consuming process. So that is the problem initially, right? Now, what would be nice to do, now this is a very busy slide, but the only thing I want to point out is that in the standard, this is a standard drug discovery pipeline, okay? In the standard drug discovery pipeline, what quantum computers can do is to be able to discover the hit, so discover and optimize really the molecule, okay? So this is what you would like to do on a computer or an hybrid quantum and classical computer, because this would allow you to already start testing on a much more, let's say, precise and accurate molecule. So you want to create something which is called in silico drug discovery part, okay? So you want to be able to do this not by trial and error in the lab, but on a computer. That's the goal. And this is what we are aiming at doing. Now, once you do this incidentally, you will not just solve a problem for photodynamic therapy, but there are many other problems that can be solved if you have this type of computational pipeline, quantum boosted computational pipeline. And so therefore you add the value for many, not just for one problem, but for many. Remember, that's the value of having a software platform, that you can solve not just one problem, but many, okay? And this is what actually creates true value in general. Now, this is the point in which I go in the details, and I'm going to tell you how this is done on a quantum computer, because we have an end-to-end working pipeline for a molecule that is one of the candidates, photosensitizer, one of the candidate molecules for photodynamic therapy. This is, well, it has a name, TLD, it doesn't matter. Okay, you see it here, this is its composition. Now, this molecule is in phase 2 clinical trial. So there is a biotech that has brought this molecule in clinical trial. However, in order to manipulate the properties of this molecule, you have to change certain things, and I will tell you what are these things. So I make a simple example. Look at skin cancer or bladder cancer. So for skin cancer is very superficial. So the light does not need to penetrate much in depth. It has to penetrate. So the wavelength of the light that you need to use for skin cancer is very different from the wavelength of the light that you have to use for bladder cancer. And the mechanisms that allow somehow the release of ROS, that allows to kill the cancer cells are very different. So I will tell you in a very simplified way, the molecular structure that you have to consider. This is like a super simplified model, but it identifies the key points. You have a ground state, you have an excited state, and you have two exciting states. And so you have to look at the energy differences and optimize these energy differences between this S2S transition and this singlet triplet transition. This is a spin orbit coupling. Okay, so this is you have to calculate molecular properties which are related to observables precisely connected to this specific electronic structure eventually, okay? And you do this in practice. What they do in the lab is that they attach to this molecule additional motifs. So it's very, instead you want to do this computationally. Okay? You want to calculate this property computation. Now, if you do this, look at this. This part here, the upper part is pre-processing. The lower part is post-processing. So this means that, and then this part here is that what you actually do on the quantum computer. So you see that the majority of the algorithm is all done on classical HPC. And then you run what you cannot do, what is the hard problem on the quantum computer. And why this is a good problem for a quantum computer? Because it's not just really the calculation. First of all, because there are very strong correlations in this molecule. This is for chemists. This is a ruthenium-based complex. In the center, there is a heavy metal. There are relativistic effects, a very complex system. So, and it is impossible to describe very precisely all these energy gaps and these phenomena classically. So it's an inherently quantum mechanical problem. So you have not only the need from the end user, but you also have the reason why it should be done on a quantum computer, because it's fundamentally quantum and there are strong correlations that comes to play. So what you need to do is first, this first part are parts that really chemists do in their normal routine, okay? The first part is a part in which you somehow take into account that the molecules are not isolated. They are surrounded by solvents, they are surrounded by their environment, and so you have techniques for doing these so-called embeddings, so considering also the effect of the environment, not only the effect of the molecule. Then you have to select the active space, so molecules have many, many, many electronic states, and you have to select those that are only relevant in the sense that where there is all the entanglement, if you want, is concentrated. And so there are techniques to do this. It's not simple in a way that is automized or semi-automized. Then you have to prepare the excited state, right? And you have to prepare an excited or ground or excited state. In this case, remember, we have one ground state and two excited state, two singlet and one triplet. And you have to do this in a way that is sufficiently close to really what you want to calculate. So it cannot be a random state, okay, obviously, because it has to be, otherwise you will be looking like in a vast space. So it has to be very precisely done. Then you have to measure in a way that is optimal. Then you have to remove the errors, and then you have to calculate the molecular property. Now, and of course, this is only the point in which you run a circuit and measure. That's the only thing you do on quantum computing eventually. And I will now give very brief key points. The first one is that all these stages, they need to be optimized, but they are not independent from each other. So you need to optimize them all consistently. An example, I will look as an example to these three parts, the state circuit preparation, okay? I start with this one. So we have discovered an algorithm which is published here. It's called the Majorana propagation, which allows us to create efficient circuits for quantum chemistry initialization at large scale. I will not give the detail, but it's an approximate technique that allows basically to implement variational quantum eigensolvers like algorithms, but not on the quantum computer, in pre-processing, all on the classical computer. We are able to benchmark this. So these are some numbers. This is for 28 qubits, 40 qubits, 52 qubits. It's all classical, okay? And we are able to benchmark it. This is how long it takes with our algorithm. Okay, the pre-processing is 0.32 seconds, and the estimation is of this order. So it's really, really fast. If you use instead Qiskit state vector simulation, it's 3 hours. Q and Q with MPS. I mean, it is extremely fast with respect to the competing alternatives. And this is what allows actually to scale. For 52 qubits, there is no way of doing this simulation, neither with Qiskit nor with Q. We were unable to do it for the same accuracy, of course, that you want. And this, by the way, is not just useful now. This is the same problem that you will have if you want to use phase estimation on a fault-tolerant chemistry platform. You will have exactly the same problem. You just cannot start with just a random initial state. You have to very precisely generate the right state. Second point, the scaling. So why this wall method is meaningful? Because the best classical method in chemistry for doing precisely the same things is called the DMRG, it's a tensor network-based method. And for this molecule, the classical method scales exponentially. Okay? So you see here an exponential scaling, and this is the regime which is required to have good accuracy for the optimization. So there is a need because you have an exponential scaling, so you cannot afford this anymore when you go in the regime of 100 qubits, while our old pipeline has a scaling which is polynomial. This is for the three state, S1, S0, and T. So that's basically an example of why this problem is meaningful on a quantum classical hardware with respect to the classical alternative. Because you have a problem which is exponential, while in the hybrid pipeline that I just described to you becomes polynomial. So you have the possibility of actually implementing. And finally, I will not say much about the error mitigation because I'm already over time and I want to go for questions, but there are ways to describe the error mitigation, which is again based on tensor network methods. I will just not mention anything. They are based on basically the same chemistry algorithms, but boosted by quantum computing. Now, the final point, because it's the thing which is closest to our heart, is the measurements, okay? If you look at how you measure, here I have S0, S1, and T1 are again the three electronic states, and here I compare. You have here the number of measurement shots to chemical precision, the number of measurement shots you have to do to achieve a precision which is okay for chemistry. And you see the standard, this is for 16, 28, 40 qubits and so on. And I compare the standard way of measuring, which is classical shadows for those of you who knows it, with our optimized methods. And if you look at these differences become huge. So in practice, if you want to study or work with 100 qubits, you have an improvement up to 18 orders of magnitude if you know how to measure properly, which is exactly what we are doing. So this is a difference between something which is prohibitive and something which can be implemented because it's in the order of measurement shots of the order of million, 10 millions that can be actually in the short, near term implemented on quantum computing. So overall, the message is that in order to do something so complex as what I just said, you need to optimize all these layers. You need to have developed all these layers. And you need to have aligned an end user need with the capability of quantum computer today with a clear direction on how to scale. Soon, the chemistry pipeline will be available on Qiskit function as it is the error mitigation, in fact, in June this year. And of course, this is the team behind all these improvements, the co-founders, and the whole Algorithmiq team. And with this, I thank you for listening. Thank you.
Oh, thanks for a great talk. And questions from the audience? Oh, go ahead. There's a microphone there.
Yeah, hi. Thanks for a great talk. Yeah, so I think I missed the actual method for the energy evaluation in the last chemistry problem. So how do you? I mean, is it like VQE or?
Yeah, the energy evaluation is done. It's actually here. So what we do is the Majorana propagation. So we use, because I didn't explain it in detail, that's why it's not that you missed it, I didn't say it. So what we do is that we So first of all, this is composed of two parts. The first one is a fermion to qubit mapping, of course. And then we have to, of course, evaluate the energy by using and generate the circuit itself that somehow approximate this ground state. And the way in which we do is, do you know the method called adapt VQE?
Yeah,
No.
VQ,
Do you know variational quantum eigensolver?
Yeah, that
yes.
one I know.
So VQE, the problem with VQE is that it's very heavy, actually, to do the full loop, the full optimization on the quantum computer and classical. So to keep optimizing between, and it's realistically, it's considered to be impossible to implement. There are many problems. There are Barren plateau problems. There are initial ansatz problems. So the second step towards a variational quantum eigensolver is a method that was, I think, firstly proposed by the group of Sofia Economou. It's called adapt VQE. And it's a VQE in which you generate the ansatz, so the circuit to implement, one layer at a time. And you keep adding layers based on the estimation of a pool of observables. So there is a large pool of observables that has to be selected properly, and it has to be estimated at each run in order to decide which gates to apply. Now, the problem with this method is that this pool is generally very large, so you have to calculate expectation values of many, many, many observables. Meaning, I think it's n to the 8, and I don't remember, it's very large. I think it's of the order of n to the n, where n is a number of qubits. The problem of these is, of course, so one way in which we go around, in principle, in general, is that when we use these informationally complete measurements with the same data, we can calculate expectation values of basically any observable and minimize the variance. But okay, here we don't even do it in practice. What we do is that we calculate them basically utilizing this classical approximate technique to calculate the electronic dynamics. So we can classically, layer by layer, do adapt VQE, and therefore then only at the end implement the circuit. It's a very complex method, and I cannot explain it. I'm happy to discuss it more in detail, but I cannot explain it in detail. The most important thing is that really, I mean, all this that you see here, in particular here, you see, this is the state error means the overlap for 28 qubits, 40 qubits, 52 qubit. This means that 10% means 90% overlap, okay, with the reference state that you actually would need to achieve. So it's an adapt VQE done classically using an approximate method that is known as Majoranic propagation, and that is, we recently put on the archive, and this is the archive number. That is the best I can say. I mean, there are many details, but it's a very, it does not, importantly, it does not replace, it doesn't mean that you can simulate the whole, you know, the whole chemistry problem. It just, you can simulate only the energy. You can obtain efficient estimation only of the energy, not of the RDMs.
But yeah, but then what is the role of the quantum? So you generate, okay,
yeah.
So very good circuit or ansatz classically.
Yes.
And then the quantum circuit is then, so same circuit is measured, and that energy is then taken as
it's very, very good point. Yes,
as the answer, and that which is then after error mitigation becomes better than the classical.
Yeah, it's a very good point. Yes. So the answer to this is that you don't have the exact state. You cannot really have the state. Okay, you just have a good estimation of the energy. But of course, in order to do all of the things that I mentioned there, you need to calculate properties. So you need all the RDMs, so the reduced density matrices that are needed in order to calculate all the chemistry property require really a quantum computer. So eventually you will need to have a method that allows to extract RDMs, not just the energy, okay?
Yeah, but the energy, okay. So the Majorana only, this classical Majorana propagation only gives you the energy.
Yes.
Not, so
it doesn't give you all the RDMs, it doesn't give you all the state, obviously. So that's why you need to have, you need to use it in order to, you can have a good approximation, you can use it to have a good approximation of the state. Obviously, you don't get the state. You have a good approximation, meaning that it has, say, 90% overlap or 80% overlap. It depends, obviously, depending on how deep you go with the adapt, you can have better or worse approximation, and that's up to you. It's a question of resources. But then, of course, you will need to sample from the state on the quantum computer. That's why you have to generate the state, and then you have to sample. This you cannot replace. The sampling must be done, and this is what is needed then to calculate all the properties that are needed for the spin-orbit couplings, the energy difference. Everything needs to be done then on the real quantum computer. So it is not replacing. It is not. Initially we thought, wow. I mean, if you do this, I mean, do you actually need a quantum computer at all? But you do need it, actually, because you need the state, you need to sample from the state, and then you have to, after that, we do, in post-processing, we move towards what is the real state, or what are the real properties, but we do it in post-processing.
Okay, great, thank you.
Thank you.
The M2, M3, whatever, on the top line, what are those M?
Oh, I think these are the Majoranic, the monomials that are, I didn't say anything about it.
Okay.
Yeah, this is, yeah. These slides was simply to tell you that there is, I want to put a picture and tell you that there is a paper, and this is an approximate method. That's the only message.
Is this similar to unitary evolution? Can you have a
it's actually, no, I mean,
apply unitary matrix and evolve?
And the key part is this, you see, at some point there's a cut, coefficient truncation.
Mm-hmm.
So the way in which these monomials evolve, I mean, in time, has a certain structure. And it turns out that those terms of, I think, lowest weight, they never come back. So it's like statistically, you can cut these parts. So you are able to, from a statistical argument, to only keep a few leading terms in the dynamics. So it's basically, it's a combination of somehow statistical arguments and analysis of how these things propagates, basically. I mean, said in a very, very simple manner, okay? It's an approximate method. It doesn't hold for all types of, obviously, it's important to mention. It's for fermionic systems, but it's also specifically, it uses some assumptions on the form of the Hamiltonian of the, on the electronic structure problem. In particular, it's good for chemistry. It's not good for like brickwork circuits, for example. So chemistry Hamiltonian are sparse. So there are specific conditions that need to be satisfied for this method to work well. But if some of the people in the audience know, for example, belief propagation, there are some similar methods for spins that have been recently discovered. And this is a similar one, but for electronic systems, or for fermionic systems.
Any questions from the audience, the Zoom out audience? If you do, you can speak right away. Oh, go ahead.
Hi, thank you for a very nice talk. So I have a question because if I understand correctly, all of these error mitigation strategies that you're using are an alternative to quantum error correction now that we don't have fault-tolerant quantum computers, but do these methods survive once we have a fault-tolerant quantum computer, or they could be merged? Or?
Yes, that's a very, very important question, and this is indeed something that we are already doing with two companies. One I can mention, the other not, but the one I can mention is QCI, that is Quantum Circuit Inc., from the Rob Sholkoff guy, big superconducting qubit, Yale professor. And there, what they've done is that they have a different type of qubit architecture. It's called the dual rail qubit that is inherently allows to do some error detection. And with them, we are working on, actually, we already have some results in which we can combine error mitigation with their error detection. So, and this is not the error mitigation. The first example I showed is more the one I didn't show, which is more similar to the MRG, let's put it in this way. If I'm right, we don't use TEM, no? Okay. I think we use the T-night, which is, yes, QCI, yeah, okay. So I'm right, it's not. But anyways, it's also a tensor network with mirror. So the message is absolutely yes. I think that there will be many ways in which you will combine, we are already exploring it now, for sure for early fault-tolerant quantum computers, but also, my opinion, of course, this I don't know, in the future, it could also be that really depending on the problem, and if you have very, very small average error per qubit per gate, you may have your quantum computer divided in parts. There are those where you do error correction and those where it's sufficient to use physical qubits with error mitigation. Just because, I mean, in the end, it's a question of calculating resources and seeing what makes most sense. And in some cases, you may not, it may be just too much to use the full error detection or error correction, but you can use more physical qubits with error mitigation. They could be, or they could be integrated into pipelines. So this, of course, is more speculative as an answer, but already now we think that you can use, for example, you can, if you have partial error correction, you can use at the end, after the partial error correction, you can use the error mitigation, because this method that we have, they are, so error mitigation with tensor networks, you can prove that the smaller is the error, the easier is the error mitigation. So in the case of a tensor network, it's like the bond dimension of the tensor network method is becomes smaller and smaller for more and more, let's say, cleaner and cleaner qubits and gates. So then it could be used, for example, at the end of a partly error-corrected method, just to remove the remaining errors. So there are many ways in which you can do it. Yeah.
Any more questions? Or if not, then we can thank the speaker for a great talk. And
thank you.